Hello, welcome back. Thanks for coming again, still being here. Well done, second week in a row. So today is borrow checking and the moves, ownership, all that jazz. This is the hard part. This kind of stuff is the reason that Rust is notorious for having a high learning curve. But I'm going to try and make it as easy as possible and kind of explain it in terms that a lot of you will hopefully already be familiar with, and it won't be so bad. I've got no slides for today. I'm going old-fashioned with a text editor and a terminal. Oh, what are you doing, Owen?
It's going to fiddle with the lighting.
Oh, no.
The problem is, it's only on or off. Off. Okay.
Let's call it cinematic.
Yeah.
Can that be read? Borrow checking. Let's start with the basics. Hopefully you're all familiar with the concept of program scope. So this is a program with two variables. These variables have a scope associated with them. So we have S here. This is our first variable. S is declared here, and it goes out of scope when the brace closes. There's nothing in scope at the top. Then S is in scope here. S goes out of scope at the bottom here. Rust uses brace scoping, block scoping, like every other language. We have another variable N. Like I said, it's brace scoped, so N is not in scope here. N comes into scope here and is declared and is valid from there. And then N goes out of scope when this brace closes. So at this point here, N is not in scope, but S is. Does that make sense? Yeah? Yeah. Cool. So that's scope. That's important because that is how Rust manages memory. Rust has no garbage collector. Memory is managed through a set of rules enforced by the compiler, ownership rules. Every value in Rust has a variable that is that value's owner. There can only ever be one owner at a time, and when the owning variable goes out of scope, that value will be dropped. And by drop, we mean it's destroyed, it's destructed, it's gone from the program. So when S goes out of scope here, it's destroyed, it's dropped, as we say. When N goes out of scope here, that's dropped. So we're going to use strings as an example today, mostly. We touched on strings a bit last week because strings are hard. We have a few kinds of string. So we'll learn now a little bit about the difference between some of those. So this is a string literal we have in this program. So we've written the string there. It's literally there. It's a literal. So the data for this string is stored directly in the binary file. Nothing about the contents of this string depends on anything that's going to happen at runtime. So if I compile this, I'm not going to use cargo today. I'm just going to use rustc directly. So that's printed straight there. We didn't give any input. There was no input to that program. The string is in the binary file. And we can verify this because if we use the strings command to get every string that's in the file, and then grep for hello, we find it. It's there. It's directly embedded in the binary. Does that make sense? Yeah? Cool. So our other type of string is our capital S string, which we touched on a bit more last week. This string stores data on the heap. Is anyone not familiar with the concept of the stack and the heap? OK, cool. I'll touch on it then. So the heap is a large pool of memory available to a running process. Programs can choose to store stuff on the heap, and heap data, memory on the heap, can have an arbitrary size, and you can do what you want with it. It's just a big block of memory for you to do as you please with. However, most data goes on the stack, which stores data local to a function. A function has a stack frame, which contains everything that function needs, and those frames are popped on and off the stack as the functions are called and exited. Stack sizes have to be known at compile time. So we can't allocate manually onto the stack at runtime. Local scope stuff goes on there, but if there's anything that we don't know the size of at compile time, it needs to go on the heap. So this string, we don't know the size of it at compile time. In this case, we do, but usually we could take some input here and create a string from it. And we can also push data to it however many times we want. So this kind of string uses data on the heap. Because we're using data on the heap, we need to allocate it manually when we create it. We need to ask for more space from the operating system when we grow the string. To allocate memory on the heap, we have to ask the operating system very nicely. And also, when we're done with data on the heap, we need to free it. We need to tell the operating system that we're done with it and that it can have it back. In C, you need to do this manually. I'm sure you're familiar with, most of you, mallocing, freeing, realloc, that kind of thing. In Rust, this is all done for us. So this string from call is the equivalent of your malloc. This push str call is the equivalent of your realloc. And then your free is done automatically when the string is dropped. And it's dropped because it goes out of scope. As I said, all this is abstracted away. This is a concept we call zero-cost abstraction in Rust. Details are abstracted away, and it's done for us. It's free. There's no performance penalty for this. We like zero-cost abstraction. The really key bit here is that all this data is freed automatically when the program ends, when it goes out of scope. Does that make sense? Is everyone still with me today? Any questions? Not that I can see anyone's hands up, but I think we're good. OK, cool. So now I have a question for you. What do you think happens? What do you think happens with this? What do you think happens here? So we have two variables, x and y, and one value. What do you think line 3 does? Any takers? Go on.
It copies the contents of x to y.
It copies so the value 5 is copied into y. Yeah. What about line 7? Can anyone tell me what line 7 does? Go on. Yeah, creates a variable to refer to S1. But what does that string from function do?
It just create hello in the pool.
Yes, that's our create memory. Good, that was a test. This is the hard one. What does this do? Not Felix. Felix knows. Go on.
It moves the value contained in S1 into S2, and so S1 is no longer valid.
Well done. Good answer, because that's what happens. So 5. X is 5, and then x is copied into y, x and y both equal 5. S1 is equal to our hello string, and when we reassign S1 to S2, S1 is no longer valid, and S2 contains our string. Let me show you a little example. This is what your string value looks like. Sorry, a bit bright, yeah. Should have got the dark mode PNGs. This is what your string looks like. This S1 on the left is a struct. That goes on the heap, and it's just a pointer. No, S1 goes on the stack, sorry, and it's a pointer to our data on the heap. So when so to copy, if we wanted to copy the string, there's a few different ways we could go about this. We could do this. We could copy our string, and we copy the contents of the stack, and when we do that, we also copy the contents of the heap. So if we wanted to just reassign variables like this, why don't we do this? Expensive, yes. We don't know how long our string is. It's an arbitrary size. It could take us forever. So our other alternative is this. What does this do? This copies our struct on the stack, copies our stack data, but it just copies the pointer to the heap, and it leaves the heap data. Why don't we do this? We could have dangling pointers.
Then you can have two mutable references to the same bit of data.
You would have two mutable references to the same bit of data.
You don't want to free it twice afterwards.
That's the key bit. We could have both of those things, and those are both issues, but we don't want to free it twice, because when S1 and S2 both go out of scope, they will both call free to free the data on the heap. And if you do that, lots of bad things will happen. It's called undefined behavior in C. If your C programs ever crash, this is probably why. So yeah, those are our different models of copies. But what we do instead is a move. So what our copy, our reassignment looks like is we have our S1, and we do that copy where we only copy the stack data. Data stays on the heap, but this S1 is invalidated. And if we try to use it, the compiler will stop us and go, no, you've moved that, it's gone, don't touch it. Does that make sense?
Yeah.
Good. So, copies and moves. So the reason why we use move for some things and copy for some other things is because integers and other numerical types are cheap to copy. It costs basically nothing to copy them, and it's more effort to deal with the whole move stuff. So for types which are small or cheap to copy, typically less than 64 bits, have a known size at compile time, so we can't copy this string because we don't know how big it's going to be, and live entirely on the stack, so it doesn't have any pointers to anything. Rust will copy by default instead of moving. So numbers, booleans, floats, chars, and also tuples, which contain numbers, booleans, floats, or chars only, they're all copy. You don't have to worry about moving them. Move semantics only come into play for more complex types, longer types, strings, arrays, and anything you implement yourself. So last week you did the tic-tac-toe thing. For the types you wrote, who wrote a little player type like XO enum, yeah? Yeah, you put copy clone above that, didn't you? Yeah. If you didn't put copy clone above that, you'd have to worry about move semantics for it and worrying about, oh, I've moved my player here, now this player is invalid. So you can derive copy semantics for your own types, and that's what deriving copy and clone does. For a little enum like that, that's generally appropriate because it has I think a unit enum like that is 8 bits in size, 1 byte. But for larger types, you can't derive copy and clone for them because otherwise that would just totally kill your performance. And we want to take advantage of move semantics to give us performance. Is everyone with me still? Good. So we move values in and out of function, in and out of variables. We move to variables, we reassign stuff. But how do move semantics interact with functions? Because that's where stuff gets interesting. So we have an example here, and kind of passing a variable into a function and returning from a function follow those same move semantics as reassigning to variables. What do you think happens if we're going to compile this and run it? This is 5. So have a look at that error. Can everyone read the terminal fine, yeah? Cool. So the compiler is telling us we're trying to borrow a moved value. So this function here takes ownership of S, and then we try to print S. We can't print S because we've moved out of it. So by calling this function with a string parameter, we've taken ownership of it. So why does that happen? Because our function parameter type is string. So the string data, like the data on the, it's the same semantics as with reassigning the variable. S is moved into the function. And then when this function ends here, this function finishes, some string, which is just what S has been rebound to technically, goes out of scope. So our hello will be dropped at the end of this function. Yeah? However, this function here makes copy. That doesn't do that because obviously we have our x equals 5. It's an integer type, we copy it, so we don't need to worry about move semantics and ownership. So passing values into functions and having to move them in every time gets annoying because sometimes we kind of want to use a value temporarily and not destroy it. We'll get onto that. How could I make this compile? Which line do I need to remove to make this compile? Yeah?
Line that takes ownership.
Yeah, that will work. Just try that. Oh, I'm still there. Yeah. So if we don't take ownership of it anymore, it's still valid. Alternatively, we do get that warning, but you can ignore that. We can still take ownership of it, and it will be dropped. But because we don't use it, the compiler lets us get away with taking ownership and dropping it. So gives ownership, returns a string. So S1, so this string here, yours, is moved out of this function and into S1. S2, just a string here as usual. S3 is interesting because what it does is it takes a string S2 as a parameter, but also returns a string. So it takes the string S2 and gives it back as S3. So we're kind of moving ownership through functions here. And sometimes this is useful if you want a function to kind of consume a value and then give it back in a slightly different state, or if you're trying to thread some value through a chain of function calls. This model is useful. Should we compile this and see what happens? C6. Compiles fine. If we uncomment this line and see what the error looks like. So again, we're trying to borrow and move value here. S2 has been moved out of this function and into this function, and we can't use it anymore. But we can use S3. S3 is fine. So this S2 has essentially been rebound to S3 through this function call. So let's look at another example again. This represents a more standard pattern. We just want to kind of use a value in a function. So we have a string, and we want to calculate its length. See what happens here. Again, we're trying to borrow and move value, because this function takes S1, moves it into the function, calculates its length, and then drops it. So what we can do here is, how would we actually calculate the length of this string? We use a reference. We use a reference. So this is where we introduce borrowing. So we've had moves, and the way to get around moves is borrows. So instead of moving values everywhere, we create references to values, which are kind of like pointers, but with more compile time static checking. And a pointer or reference is basically just a value that goes, hello, I'm not the value you're looking for, but this is its address. It's over there. So it points at another value. We create a reference by putting this ampersand in front of a value. And we create a reference type by putting an ampersand in front of the usual type. I'm not going to say ampersand every time. I'll just say ref. So you know what I'm on about. Yeah, ampersand denotes a reference. So we have ref S1 creates a reference, passes into this function which accepts a reference, and that works. There you go. We can change this to be, just to prove it works. Oh, I need to compile it again. God damn. There you go. So that's how we use references to get around moves. If we wanted to change a value that we have a reference to, we can't do that. And so let's look at this example. We have hello string, and we want to add world and add exclamation. Let me compile this. Yeah. So again, like variables are immutable by default, references are immutable by default. This is good, because if you had multiple mutable references to things, you could have pointers to it everywhere, you could have values being modified everywhere, and your code becomes a nightmare. Enforcing that we can only have things looking at them and not changing them, that helps reduce bugs. So we have this ref mut, here. So ref1 is ref mut s, it's mutable reference to s. Ref2, ref mut s, mutable reference to s. The problem with this is we can't have multiple mutable references. Like I said, this is a good thing, and the reason why they're not mutable by default. We can only have one mutable reference to a value in scope at any given time. So if we wanted to add weld to this string and then add exclamation mark to this string, we'd have to have only one mutable reference. And this will be fine, this would work. I didn't actually print it there, but you get what's going on, it works. So yeah, you can have as many immutable references as you like, or you can have one mutable reference. This will get annoying, but I promise you that the compiler is trying to stop you from shooting yourself in the foot. So here's another example showing how we can't really combine mutable and immutable references. So we cannot borrow s as mutable because it's also borrowed as immutable. The compiler tells you. Error messages when it comes to references and borrow checking are very, very helpful. Read them. So it's telling us we have an immutable borrow here. We have a ref s. Mutable borrow occurs straight after it, ref mut s. And we're using that mutable borrow. So we can have two immutable references, and that then compiles fine. But why does this work? Because we have immutable reference here, we have ref s, and then we have ref mut s. But these are in the same scope. How does the compiler know that we can do this? Because it's very clever. You didn't used to be able to do this in Rust, but the borrow checker has gotten a lot smarter over the last year or so, and it can look at reference lifetimes, how long a reference lives, on a more fine-grained level than just block scope. So because we have these two references here, this is the last time those are used, so the compiler go, okay, we're not using those, which is what allows you to create this ref mut here. Does that make sense? Is everyone with me? So we have immutable references or one mutable reference. What about this? What do you think foo does? Any takers? What does foo do? Yeah?
It tries to return reference to s, which goes out of scope when foo returns.
Yeah. So s goes out of scope at the end of here, but we return a reference to it. So what do we think is going to happen here? Let's see what the compiler tells us. That's not very helpful. The compiler is trying to tell us that we need to deal with lifetimes. So, as I mentioned lifetimes earlier, references have lifetimes, and you can annotate the lifetimes as these references explicitly. We're not going to do that. But what the compiler is basically telling us that the function's return type contains a borrowed value, but there's no value for it to be borrowed from. The value it's borrowing from gets dropped, so the reference can't be valid. The compiler can tell this, and it stops you from returning what we'd call a dangling reference. This is another common source of bugs in C, and something else Rust will stop at compile time. We'll deal more with lifetimes next week, and we could kind of do some fancy trickery to make sure that this would be valid, but we're not going to deal with that now. So, we also have a special kind of reference known as a slice, which is a reference into a contiguous sequence of elements. So a pointer to an array in C is just a value. You just point to the start of it. Whereas a slice in Rust is kind of the same thing. It accomplishes the same purpose to refer to arrays, but it also contains the length. So this allows you to reference arrays not just by the start of them, but you can point to any range of them. So we have our array here, just simple five numbers. And then we have two slices. So see the syntax for creating these slices here. It's just like indexing the array, but we include a range within the brackets, and this gives us a slice back. And look at the syntax for a slice here. It's a ref into an I32 array. We can also have a mutable slice, same as we have immutable and mutable references. We have mutable and immutable slices, but same rules apply. Let's compile this and see. Because we cannot borrow A as mutable. It's not declared as mutable. So we're trying to create a mutable reference to a value that we've not declared as mutable, because remember, everything's immutable by default. So let's make that mutable. Another error, because we have references here and another reference here, so we can't create multiple references that are mixing mutable and immutable. So if we just remove that, that works. And it's telling us now it doesn't need to be mutable. Compiler warnings are helpful. So that's a little bit on slices. Here's a more practical use of a slice. So for example, if we want to pass a string to a function, and we want to get the first word of it back, we don't want to have to copy there because that's expensive and annoying. We like not copying, we like moving, and we like using references because this is what gives us performance. So we take a ref string, this function first word, we take a ref string and we return a ref str. So ref str is the string slice type. So instead of using ref string in a lot of places, if we don't have ownership of that string or we just want to refer to a bit of a string, we use ref str. This is also, again, the type of string literals because we are referring to a string that lives in the program binary somewhere. It's not ours. So this is just a for loop to return the first character of, return the first word of a string. So we return up to where the first space is. Otherwise, we just return the entire thing. So we can't borrow it as mutable because it's also borrowed as immutable. We get the first word with a ref, normal ref, no mutability, but then we tried to clear the string. So the problem is, word is borrowing s, so we can't modify s. So this is important as well, because what's happening is, someone else, another reference is looking at our value, referring to our value, we can't then modify it, because this will change what the reference is looking at and create problems. This is another common source of bugs, and Rust prevents this at compile time. Yeah, so that works. First word is hello. Yeah, so that's how slices work. That's pretty much it for borrow checking, but I do have bonus file. Traits and impulse. This is just something I wanted to run through quickly because you're going to need it for chip 8. So we have traits in Rust. A lot of you hit traits last week. Who implemented the display trait last week? Yeah? So we have lots of other traits. We can also write our own traits. So traits are a way to abstract over shared behavior. Types implement traits by defining that behavior, and then we can use traits to describe a group of types that can do things. Similar to a Java interface, they're basically identical to a Haskell type class. They're very similar to Python ABCs. So this is our trait shape, and we say, okay, this is a shape, and anything that wants to call itself a shape has to be able to return its area. Makes sense. So we have our rectangle struct, and then we implement shape for rectangle, which is just saying we want our rectangle to be a shape. But to be able to do that, we have to tell the compiler how our rectangle calls itself a shape. So it has to implement this shape behavior. So we just return the area of the rectangle. There are also regular impl blocks without traits. This is how you define functions and methods on a type. So we had our string from methods and our string new methods. This is how we do these ourselves. So we have fn new, and then you'd call this with rectangle colon new. And this creates an associated function. It's just a method. We also have shrink. So this takes the self parameter, which makes it a function that we can call. It makes it a method instead of an associated function or a static method. And we call this by rectangle.shrink. This will implicitly capture self. We have another struct circle here. Again, circle implements a new method that we can call, a new associated function that we can call, and then again, we implement shape for circle. So here's an example. We call rectangle new, and then we can call rectangle.shrink. So the difference between the colon and the dot syntax is that this captures self. So if we use self as a parameter, then we can call dot, and it will capture. When we call self, we can either do ref mut here, and it will capture it with a mutable reference. So in your function body, you'll get a mutable reference, and all the mutable borrowing rules occur. If we didn't want to modify it and just wanted to look at it, for example, getting the length, we could just do regular ref. Or if we wanted our method to move, we just do self. Yeah, so that's it for traits and impulse. This has all gone through in more detail in both the book, which I encourage you again to have a look at, and in the notes on the website. Yeah, so that is it for demos, live code. I'll turn the lights back on because there we go. Ooh, welcome back. Yeah, thank you. I hope that was a decent introduction to borrow checking and you're not all too confused. But this is one of those things that as you play with, you will gain an intuition for it, and I would recommend that you do that. Again, look at the examples in the notes. Those are all runnable. Write your own little toy programs. So chip 8. We're going to go and write our own chip 8 interpreter. Same as last week, instructions for that are all on rs118.uwcs.co.uk. With the projects for the chip 8 and the Raytracer, we have T-shirts to give away. Ooh. Anyone who implements like a cool extension to the project will win a T-shirt. So we've only implemented the basic chip 8 instructions in our example. If you want to go ahead and implement the chip 8 extensions or make the display bigger or make the way chip 8 draws pixels is a little bit dodgy, there's ways to make that smoother if you want to go ahead and do that. Any cool extensions, you win a limited edition Compsoc T-shirt. I think that's it. So head over to DCS and get some pizza and build some chip 8. And if you have any questions, please come and talk to me. Thank you. We're done.
The link is in the Discord channel, so if you're on our server.
Yeah, get on Discord.